In 1969, NASA put 2 humans on the surface of the Moon. They had been working on the problem for less than 9 years. The computers that guided them there had less processing power than a modern pocket calculator. The engineers who designed the spacecraft used slide rules. In 2026, NASA finally sent humans back to the vicinity of the Moon. Artemis II, the first crewed lunar mission since 1972. It took over 20 years. Modern computers, modern materials, modern simulation, modern manufacturing. And none of it made the problem easier. It made it harder. This video is about why, not the politics, not the budget fights. The engineering reason, the one that explains why having better tools can actually make a harder problem. We'll start with what Apollo actually accomplished, because most people misremember it. Then we'll trace what disappeared after it ended. Knowledge, factories, entire industries. And we'll arrive at a truth that extends far beyond space. Civilizations can lose the ability to do the hardest things they've ever done, even when they still remember how. Here is the assumption almost everyone makes. Apollo proved it was possible. Modern technology should make round 2 easier. Better computers, better materials, better simulation. Just rebuild what worked with modern parts. Same trip, same destination, same physics. This assumption is wrong in almost every important way, and the reasons it is wrong tell us how knowledge actually works and how quietly it can disappear. In May 1961, the total amount of American human spaceflight experience was 15 minutes. 1 suborbital hop. Alan Shepard, up and down. From that starting point, Kennedy committed the country to landing on the Moon within the decade. What followed was the largest peacetime engineering mobilization in history. At its peak in 1966, the Apollo program employed roughly 400,000 people. It consumed 4% of the entire federal budget, roughly $280 billion in today's money. New rockets, new spacecraft, new spacesuits, new navigation, new manufacturing techniques, new ground tracking systems. None of it existed in 1961. All of it had to be invented, built, tested, and made operational in 8 years. What that investment built was the Saturn V, a 363-foot rocket, 6.5 million pounds at liftoff, capable of throwing 50 tons toward the Moon. The F1 engines powering its first stage each produced 1.5 million pounds of thrust. 5 of them ran simultaneously. They remain to this day the most powerful single-chamber liquid-fuel rocket engines ever built. And the lunar module, the spacecraft that actually landed on the surface, weighed only 33,500 pounds and carried 2 astronauts down and back using propulsion systems simple enough to work reliably. Every one of these machines was designed, tested, and flown within a single decade. And then it ended. Apollo 17 left the lunar surface in December 1972. The last Saturn V flew in 1973, carrying Skylab into orbit. The production lines were closed, the tooling was mothballed or scrapped. The workforce dispersed into other programs, other industries, retirement. Within 5 years, the most capable deep space transportation system ever built had been quietly dismantled. Not because it failed, because the country decided it no longer needed it. You cannot just start again, because what disappeared was not just hardware. In 2013, a team at NASA's Marshall Space Flight Center pulled a surviving F1 engine out of museum storage. They wanted to study it. They had the original engineering drawings. They had finished hardware. And yet, they found that the documentation was incomplete. The drawings showed what to build. They did not show how to build it. The manufacturing techniques lived in their hands, in their judgment. That kind of knowledge resists being written down. It is learned by doing, maintained by practice, and lost by stopping. By 2013, most of those engineers were dead. This pattern repeated across the entire Apollo legacy. The Saturn V's massive welding fixtures and assembly jigs were destroyed in the 1970s. Its electronics used vacuum tubes and discrete transistors that no manufacturer produces today. The lunar module's hand-built techniques were never formally documented. Even with every Apollo blueprint, you cannot walk into a factory today and rebuild a Saturn V. You would have to reinvent half of it from scratch. This is not a NASA failure. This is what happens to any industrial knowledge when the hands that hold it stop practicing. Knowledge that is not actively used does not wait. It fades. It wasn't only knowledge, it was infrastructure. In the 1960s, the US had an industrial base capable of producing 12 Saturn V rockets per year. Dozens of prime contractors and hundreds of subcontractors maintained dedicated manufacturing lines for deep space hardware. By 1980, those lines were gone. The shuttle program, which replaced Apollo, used entirely different rockets, entirely different spacecraft, entirely different manufacturing processes. Supplier relationships dissolved, skilled workers moved to other industries, institutional memory evaporated. By the time NASA needed a heavy lift rocket again for Artemis, the industrial capability that had built Saturn V no longer existed in any recognizable form. The Space Launch System, the rocket that carried Artemis II, cost roughly $23 billion to develop. Each launch costs approximately $4 billion. A Saturn V launch, adjusted for inflation, cost about $1.5 billion. The modern rocket is more than twice as expensive per flight, because much of that $23 billion went to rebuilding industrial capability that no longer existed. Qualifying new suppliers, training new workers, validating manufacturing processes that hadn't been performed in decades, certifying components for human spaceflight from scratch. None of that work would have been necessary in 1969, when the factories existed, the workers existed, and the supply chains were active. By 2010, they did not, and the cost of bringing them back was enormous. Modern human spaceflight demands multiple redundant systems, complete failure mode analysis for every component, software certified to standards that did not exist in the 1960s, and safety reviews at every milestone that can take months or years. Each of these requirements exists for good reason. They save lives. But the result is hardware that takes far longer to design, costs far more to build, and moves far more slowly through development. Artemis engineers cannot do this. Every design decision must survive years of review before it reaches a launch pad. Apollo accepted risks that no modern human spaceflight program could accept. The Apollo 1 fire killed 3 astronauts during a ground test. Apollo 13 nearly killed 3 more during transit. The lunar module was designed for a single landing attempt. If the engine failed to ignite, there was no abort. Modern flight demands multiple redundant systems and complete failure mode analysis. These save lives, but the result is hardware that takes far longer to design. Apollo's engineers could build a component, test it, fly it, see what broke, and fix it for the next flight. That iterative speed was the engine of the program. Artemis engineers cannot do this. Every design decision must survive years of review before it reaches a launch pad. Apollo's guidance computer had 64 kilobytes of memory. Its entire software could be read and understood by a single engineer. They knew what it would do. Orion's flight computer runs millions of lines of code that no single engineer can fully comprehend. It is vastly more capable, but vastly more difficult to certify. Apollo achieved confidence through simplicity. Artemis must achieve it through years of integration work. More capability required more time. So this is the context in which Artemis II should be understood. It did not simply repeat Apollo with better tools. It rebuilt the capacity to do what Apollo did, from an industrial base that had largely ceased to exist. The Space Launch System uses friction stir welding instead of the riveted joints of Saturn V. Modern composite materials instead of 1960s aluminum alloys. Computer-controlled precision machining instead of hand-fitted assembly. None of it is Apollo hardware. It was all designed, qualified, and manufactured fresh. Artemis II is proof that the rebuild worked. But there is one thing Artemis has not rebuilt: scale. NASA can currently build SLS rockets at a rate of roughly 1 per year, half the rate of Apollo 60 years ago. The rebuilt industrial base is smaller and more fragile than the one Apollo built with wartime urgency. The capability has been restored, the scale has not. Here is what the 53-year gap between Apollo 17 and Artemis II actually represents. Not a failure to progress, a demonstration of how hard it is to maintain the hardest things a civilization can do. The United States in 1969 had the capability to send humans to the moon. By 1980, that capability had begun to erode. By 2010, it was nearly gone. By 2026, after 2 decades of effort and tens of billions of dollars, it had been partially rebuilt. Capability is not just knowing how, it is the entire system that turns knowing into doing. Blueprints and physics are only the beginning. Apollo was a sprint powered by national urgency and unlimited resources. Artemis was a marathon powered by persistence against budget constraints and institutional inertia. Both worked, but the gap between them is a warning. The hardest things we can do are also the easiest things to lose, not through forgetting, but through stopping. Starting again costs more than continuing. It costs more than continuing ever would have. Subscribe. We explain the hidden engineering, biology, and physics behind the things you see every day.